Hello and welcome to a new video on IGCSE Classified Physics Paper 4. In this video, we shall be discussing the topic of charge and current. We shall be focusing on the equation Q equals I times T. Of course, Q here represents charge, electric charge. I represents electric current, and T represents the time. And this tells us that the current multiplied by the time gives us the charge. And you should understand that this comes from the definition of what a current is, because a current is essentially the rate of flow of electric charge. When we say rate, this means that it is something divided by time. So here we say that current is charge divided by time. And this is where the equation Q equals IT or I times T comes from. Because if we take the T to the other side mathematically, we get the equation at the top. And this is the subject of our video. We shall be dealing with problems that handle this issue. There is a current of 0.29 amperes in an electrical circuit. Calculate the time taken for a charge of 15 coulombs to flow through the electric circuit. So again, we always start with the equation Q equals IT. I don't like to memorize different variants of the same equation, so I just take one variant and I memorize it, and I know how to transform it into any other shape depending on what I am required to find. So in this case, we are required to find the time. We have the equation Q equals IT. We want time to be alone so that we calculate it. So we can divide by I, we can take the I to the other side in the denominator, and we get the equation T equals Q divided by I. And then we simply substitute the given values in order to find the time. So Q is the charge measured in coulombs. So this is equal to 15 divided by the current, which is 0.29. And we simply divide 15 by 0.29, and we get 51.7. Of course, we like to approximate to two significant figures. So 51.7 becomes 52 seconds. The charge on the sphere in B is 2 times 10 power negative 5 coulombs. A high resistance wire is now connected between the sphere and the Earth. It takes 20 minutes for the sphere to become completely discharged through the wire. Suggest why there is a current in the wire between the sphere and the Earth. Because the sphere has a positive charge, and this attracts electrons from the Earth, so there is a current. So this can be explained in more detail if you refer to our previous video on electrostatics, where if we have a charged sphere that has more positive charges and we connect an Earth wire, we expect the negative charges to flow from the Earth and into the sphere. This was previously discussed in great detail in another video that I recommend that you refer to in case this is confusing for you. In double I, we're asked to calculate the average current in the wire between the sphere and the Earth. Now, like I said, I just memorized one form of the equation, which is Q equals I times T. Here we want the current, so we want I to be alone. So therefore, we will divide by T. So T goes into the denominator beneath Q. So now we have I equals Q over T, and we simply plug in the given values. So the charge given in coulombs is 2 times 10 power negative 5, and the time is 20 minutes. So minutes is not a basic unit. We have to convert it into seconds. We have to multiply here by 60 in order to find the correct value. And if we perform this operation on the calculator, we get a value of 1.7 times 10 to the power of negative 8 amperes. A charge of 7 coulombs flows along a wire in 5 minutes. Calculate the current in the wire. Again, we begin with the equation Q equals I multiplied by T. We want to find current, so we divide here by T to get rid of the T. Now we have I alone on one side, so I equals Q over T. And we can plug in the required values, which are 7 and 5, but 5 is in minutes, so we have to multiply by 60 to convert to seconds. And then we plug this into the calculator, and we get 0.023 amperes. When fully charged, a 1.2 rechargeable battery can deliver a current of 210 milliamperes for 10 hours. Calculate the charge that can be delivered by the fully charged battery. So in this case, we will start with the basic equation as well. And here we are required to calculate the charge. So we want Q. So there is no need to play around with the equation since the variable that we're looking for is the isolated variable in the equation. Q is already alone and we want Q. So we simply plug in the values that we're given. We're given the current is 210 milliamperes. So 210 divided by 1000 because it's milliamperes. There's a small m here. So to convert it to amperes, you have to divide it by 1000. You get 0.21 amperes, and then you plug this into the I. So I becomes 0.21. And the time given here is 10 hours. So in order to get it in seconds, you have to multiply by 60 and then multiply by 60 again to go from hours to minutes and then to go from minutes to seconds. You have to multiply by 60 twice. So this is going to be 10 times 3,600. And this is 36,000, of course. And then you multiply this number by the value that you got for I. And this is what we did here. And we got 7,560. We usually like to have two significant figures only. So we convert it into 7,600 coulombs. And that is our final answer for question I. In double I, we are required to calculate the energy stored in the battery when fully charged. So you should know that the potential difference V is the energy per unit charge. So V equals E divided by Q, energy per charge, so energy divided by charge. And we want to calculate the energy, so we want to rewrite the equation so that energy is alone. So energy equals, we take the Q to the other side, it becomes multiplied by V. So E equals V times Q. And then we simply plug in the values. V is 1.2 volts. It is given in the question here. And Q is the number that we got, which is 7,600. So you multiply these two together in order to get the value of the energy, which is 9,120. And then we approximate to two significant figures. So we get 9,100 joules. In triple I, we are asked to find or to state the type of energy stored when the battery is charged. You should understand that a battery stores chemical energy. Moving on. The current in an electrical device is 0.21 amperes. Calculate the charge that flows during a 75-second period of time. So from the units, you should know that this is current, of course, and this is time. And the rule says Q equals IT. And we want to find the charge. So we're looking for this, and this is already isolated. We don't need to play around with the equation. So we simply have to plug in the values. And there are no conversions here. This is ampere and this is seconds. So we have the units that we want. We don't need to convert any units. So we just multiply 0.21 times 75. And this gives us 16 coulombs. Next, we move on to comprehensive questions that integrate charges, moving charges with conducting spheres, and the equation Q equals IT. So this is comprehensive questions on electrostatics in general. Here we have a ball, a conducting ball that oscillates between two charged plates. So oscillates means that it basically moves back and forth, moves to the right, and then moves to the left, and then moves to the right again, and so on and so forth. The ball repeatedly strikes each plate in turn. Explain in terms of charge on the ball why the ball moves to the positive plate after striking the negative plate. We saw a similar question to this on the video on electrostatics. We said that once the ball hits the negative plate, it acquires negative charges. When it acquires negative charges, it is repelled from the negative plate because negative and negative repel each other. So the ball is going to move to the left and it will be attracted to the positive plate. Once it reaches the positive plate, the negative charges on the ball are going to move out of the ball and into the plate. So the ball will become positively charged. Once the ball becomes positively charged, it is now repelled from the positive and attracted to the negative. So it goes back to the red position, and so on and so forth. So we want to explain why it moves to the positive plate, and the reason is that it acquires electrons after hitting the negative plate. It acquires electrons, so it becomes negatively charged. Hence, it is attracted to the positive plate. In question B, we are told, state which particles move through the sensitive emitter and the direction in which they move. So we have positive charges here, and you should know that positive charges are heavy, while negative charges are light. So definitely the charges that move are the negative charges or the electrons. And in order to figure out the direction, you should understand that this is sort of like a battery, but with very high voltage. So we have a positive charge here and a negative charge here. So if this were a battery, it would look something like this. And electrons always move from the negative plate of the battery. So we have electrons or negative charges moving in this direction and going to the negative plate to charge it up, and then moving out of the positive plate. So electrons leave the positive plate. This is why it's positively charged, and they move towards the voltage supply. So therefore, through the emitter, inside the emitter, what is the direction of motion of electrons? Obviously, from left to right. In C, we're told for each complete oscillation of the ball moving between the plates, a charge of 8.5 times 10 power negative 10 is transferred from one plate to the other. The frequency of oscillation is 4 Hertz. Calculate the current shown on the sensitive emitter. So this is a slightly different question from what we saw before, because we're supposed to use the equation Q equals IT or I times T, but we're not given the time here. We're given the charge, and we are required to find the current. So we can rewrite it as I equals Q over T. But we're still not given the time, so we cannot find T. We cannot get T directly from the question. We have to calculate it. We are given the frequency instead. And from waves, you should know that frequency is the number of cycles per second, and it's inversely proportional, or it's actually just 1 over the period of oscillations, where the period is the time of one oscillation. So in order to get the time of one oscillation, we can simply divide it by the frequency. So time equals 1 over frequency. This gets us what we want. So 1 divided by the frequency, 1 divided by 4 gives us 0.25. And now we have the time. So we can just plug it into the equation. So T is 0.25 and Q is 8.5 times 10 power negative 10. And we divide them by each other in order to get the final answer, which is 3.4 times 10 to the power of negative 9. A lightning conductor protects a tall building and the people in it against damage and injury caused by lightning strikes. The lightning conductor is a very long strip of copper that is attached to the side of the building. At the top of the building, the strip of copper is connected to a vertical metal pole, and at the bottom of the building, it is buried in the ground. The bottom of the thunder cloud is negatively charged. As the cloud moves closer to the building, the top of the metal pole becomes charged. State the sign of the charge at the top of the metal pole and explain in terms of the particles involved how it becomes charged. So like we know, negative charges would repel negative charges and attract positive charges. So if we have negative charges here, then we definitely have positive charges here. But does that mean that the positive charges moved upwards? Definitely not, because we said positive charges do not move, they are heavy. It just means that the negative charges were repelled downwards. So this is very important. A loss of electrons happened from the top. The electrons moved downwards. So this part became relatively positive because most of the electrons moved downwards. So the remaining charges here are positive charges. But it's very important to understand that the charges that move are not the positive charges, but rather the negative charges. So therefore, we have to say that it becomes positively charged. And the reason is that electrons are repelled and they move downwards. Not the positive charges that move, but the electrons. In question B, we're told, as the cloud passes over the building, a lightning strike occurs and a charge of 0.84 coulombs flows through the lightning conductor. The charge flows for 3.5 times 10 to the power of negative 5 seconds. Calculate the average current in the lightning conductor during this time. We are required to calculate current, I, and we are given time, and we have Q, which is the charge. Of course, we're going to use Q equals I times T, but we want I to be alone, so we rewrite this as I equals Q over T. We just cancel out the T and bring it to the denominator here, and then we plug the given values. So Q, or the charge, is 0.84. We write it down, and then the time is 3.5 times 10 to the power of negative 5. We write that down as well, and we perform the calculation on the calculator. We get 24,000 as a final answer. It's usually better to write big numbers in scientific notation. So 2.4 times 10 to the power of 4 amperes. In II, we're told it is suggested that the current in the lightning conductor could be measured by connecting a laboratory ammeter between the pole and the copper strip. State one reason why this cannot be successful. Of course, a laboratory ammeter is an ammeter used in the lab, so it's expecting to measure, the ammeter itself is expecting very small currents. It is designed with the expectation that very small currents will be flowing through it. It's just a circuit in the lab. So definitely a laboratory ammeter cannot handle the large amount of current that comes from a thundercloud, because a thundercloud will create a huge current. And we already calculated the value of this current. It's 24,000 amperes. However, in circuits, we usually have 5 amperes, 7 amperes, not 24,000 amperes. So therefore, the ammeter would be damaged by such a large current. Finally, we are told that the copper strip has a large cross-sectional area. State how increasing the cross-sectional area of the copper strip affects its resistance. This is a topic that will be discussed and elaborated further on in another video that has to do with the resistance of a wire. But for now, just keep in mind that the wider or the larger the area of a wire, so if I have two wires, one with a small area here, the area is small, and another one, but with a large area. So here we have a big area. If we have a big area, the resistance decreases because it's as if you have more space for the electrons to flow. So you have a smaller resistance. So this is just something to keep in mind. However, this will be discussed in greater detail in another video. A defibrillator is a machine that sends an electrical charge through the heart of a patient whose heart is not beating correctly. Doctors learn to use a defibrillator by practicing on a medical dummy. The figure shows the two contacts of a defibrillator attached to a medical dummy. The contacts that touch the dummy are made from metal, and when the defibrillator is being used, one contact becomes strongly negatively charged, and the other contact becomes strongly positively charged. The handles of the contacts are made from plastic, which is an electrical insulator. State how the structure of an electrical insulator differs from the structure of a conductor. We said this before. The electrical insulator does not have free-moving electrons. Its electrons are fixed in position. In II, we are asked to suggest why the handles are made from an electrical insulator. Of course, this is to protect the doctor from suffering from an electric shock. So we definitely need the handles to be made from an electrical insulator to avoid injury or, in some possible cases, even death. In B, we are asked to explain, in terms of the particles involved, how one contact becomes negatively charged and how the other contact becomes positively charged. It is very important to understand and to express that the moving charges are the electrons, not the positive charges. So it's very important to talk about the motion of electrons, not positive charges. So if they move out of one contact, this contact will become positively charged. The one that loses electrons becomes positively charged. And the one that gains electrons becomes negatively charged. Finally, in C, we are told that the defibrillator passes a charge of 9.1 times 10 to the power of negative 3 coulombs through the medical dummy in 6.5 times 10 to the power of negative 4 seconds. Excuse me. So here we are given the charge in coulombs. So this is Q, and this is the time in seconds. We want to find the average current in the dummy. Of course, Q equals I times T. Here we are looking to find I, so we have to rewrite the equation by dividing over the time and canceling it out from here. We have I equals Q over T, and then the units here are as needed, as required. We don't need to convert from hours to seconds or anything of the sort. So we simply copy down the values. We have 9.1 times 10 to the power of negative 3. We copy this down here, and the time is copied here. And we simply plug the values into the calculator, and this gives us a charge of 14.2 amperes, which we approximate to two significant figures. So the final answer is 14 amperes. And this brings us to the end of our video. I hope this has been beneficial. Thank you for watching.